Hello, welcome to this training module, Determining Pipe Capacity, one of a series of modules related to subsurface drainage design. Our goal with this series is to provide you with the knowledge that you need to design subsurface drainage systems and underground outlets. I'm Bruce Atherton, agricultural engineer with NRCS in Ankeny, Iowa. Let's get started. Any subsurface drainage system will have a pipe or tile that conveys the collected water to an outlet. These are called the mains. An engineering plan must specify a main with sufficient capacity to meet the drainage requirements of the system. In order to do that, we will need to be able to calculate the flow capacity of any pipe or tile. At the end of this presentation, you'll be able to 1. List the design characteristics needed to calculate the capacity of a pipe. 2. Define the variables used in Manning's equations. 3. Calculate the flow rate of a pipe using Manning's equation. 4. Calculate the area that can be drained by a pipe given the drainage coefficient. When designing a subsurface drainage system, we need to know what size and kind of pipe to use. We could ask, how big a pipe do we need in order to drain this field? Or we could ask, how many acres can we drain with an 8-inch pipe? In this presentation, we will answer the latter question. The design capacity of a drain pipe depends on 3 factors: the size or diameter of a pipe or tile, the roughness internally of the pipe, which is a reflection of the material it's made of, and the grade of the pipe. We will need to know this information to calculate the flow of any pipe or tile. The basic flow equation is expressed by this formula: Q equals A times V, where Q is the capacity or flow rate of the pipe in CFS, cubic feet per second. A is the cross-sectional area in square feet, reflecting the size of the pipe. The velocity in feet per second is a reflection of the roughness and slope. So let's determine the area for our 8-inch pipe. This may be repetition for some or all of you, but it won't take long. A equals the cross-sectional area, and this will be in square feet. For a circle, A equals pi r squared, where r is the inside radius of the pipe. Since the radius is 1/2 the diameter, we can also write the equation as pi equals d over 2 squared, or area equals pi times d squared over 4. Let's use our 8-inch tile as an example. In this case, area equals 3.14 times 4, the radius of an 8-inch tile, over 12 squared, and this equals 0.35 square feet. And this is the area of an 8-inch pipe. By convention, the maximum capacity of a drain tile or pipe is calculated using the full diameter. Let's move on to determining velocity. Manning's equation is used to determine velocity in a gravity flow situation. Manning's equation is v, the velocity, equals 1.486 divided by n times r to the 2/3 power times s to the 1/2 power, or square root. V equals the velocity, n is Manning's n, which is the roughness coefficient, and that's unitless. R is the hydraulic radius in feet, and s is the slope or hydraulic gradient in feet per foot. The roughness coefficient, n, as we said, is unitless. A lower number is equivalent to a smoother pipe, and a higher number is a rougher pipe. The numbers are very small and typically given in thousands to the thousandths. So let's look at some examples for various. This table shows common Manning's n values for various diameters of corrugated plastic pipe, which is typically used in our subsurface drainage systems and underground outlets. You can see that it ranges from 0.15 for 3 to 6 inch diameter pipe up to 0.18 for 18 inch and greater pipe. For our dual wall plastic pipe, which has a smooth interior, the common Manning's N used is 0.012. For clay or concrete tile, I typically use a Manning's N of 0.013. This is assuming normal installation conditions. Of course, sometimes clay pipe being in short sections can get off, so you might have to use a greater Manning's N, a larger Manning's N. But since we don't use much clay pipe anymore, it's not a big deal. Let's look at the hydraulic radius. The hydraulic radius is the area, cross-sectional area in square feet divided by the wetted perimeter. And this is the perimeter of the conduit or ditch touched by water. For full flow, the wetted perimeter is the circumference of the pipe, or pi times d, the diameter. As an example, for our 8-inch tile flowing full, area equals 3.14 times 4 over 12 squared, which equals 0.35 square feet. The wetted perimeter equals pi times d equals 3.14 times 8 over 12, the diameter given in feet, which equals 2.09 feet. So for the 8-inch tile, our hydraulic radius, R, equals 0.35 divided by 2.09 equals 0.167 feet. This slide represents a drawing that illustrates the ground surface in the dashed line and then a flow line of pipe. On our drawing, grade is often represented by the letter small s. Some things to note here on our drawings is that the stationing increases upstream. So our low values will be at 0 and increasing as we go upstream. We do this because the installer will typically start at the outlet and install moving upstream, and he's going to find it much easier to move with increasing stations rather than having to subtract numbers to check his work. Also note that the drawing shows stations increasing from left to right, and we do this for all of our drawings. Pipe grade should always with equations for the area and velocity of flow in a pipe known, we can combine the equations and calculate the capacity. The capacity, or Q, is equal to the area times the velocity of fluid in the pipe. So our velocity equals A times 1.486 divided by N times R to the 2/3 times the slope, or S, to the 1/2. So with our 8-inch corrugated plastic pipe, we have the area calculated previously of 0.35 square feet. We're going to use an N value of 0.015. We calculated our hydraulic radius, R, equal to 0.167 feet. And our grade is given at 0.2% or 0.02 feet per foot. Doing the calculation, we see the Q equals 0.35 times 1.486 divided by 0.015 times 0.167 to the 2/3 power times 0.002 to the 1/2 power. The bottom line here, we calculate that out, we get a capacity of the 8-inch pipe of 0.47 CFS. Well, we can do this by hand. More than likely we're going to be using software to perform our capacity calculations. This slide illustrates doing the calculation using the engineering field tools. On the lower left we can see the inputs while the output is on the lower right. In your engineering field tools software there are hydraulic formulas. The gravity flow formula that we're going to use for pipe flow is in the pipe flow section and can calculate the capacity of pipes under gravity or non-pressure flow. And you can see there on the screen that under EFT, the utilities, hydraulics formula, pipe flow, gravity flow, we can find this little box. And we can put in our pipe diameter, our water depth, which to determine the capacity of the pipe are going to be the same. We can put in our pipe slope as 0.0020 feet per foot, and Manning's end for this pipe is 0.015. The software outputs our hydraulic radius, our flow area, and our capacity, which is 0.47, which is the same as we calculated by hand. It also will output the velocity, which we'll talk about here in a little bit. Other design aids include industry slide rules, which you may have seen. Computer spreadsheets. This is a tile drainage design chart that someone set up on a computer spreadsheet, and you may have these in your field office. They work the same way as the engineering field tools. The NRCS hydraulics formula is pretty much a standalone version of the hydraulics formula that are contained in the engineering field tools, just in a different format. In Chapter 14 of the Engineering Field Handbook, there are graphical solutions. You may have seen these. And the way these work is that we can read our drain discharge in cubic feet per second over here, and our design grade in percent here to see what size pipe we need. These diagonal lines here represent the minimum or the maximum capacity of the pipe below. So a 6-inch maximum capacity would be represented by this line here, and it also shows the velocities here with these dashed lines, the maximum velocities of these pipes. So that's an option to use. We also have the Ohio NRCS design charts, which they published as a supplement to their engineering field handbook. I find these real handy to use if I need to look at something quickly. In this case, we've found our 8-inch pipe here, and we can input our design grade over here, and where they meet, we can read our design flow rate. In this chart, you can see the end value here is 0.013, so we actually have a higher capacity for the clay tile than we do for the corrugated plastic pipe. And that makes sense because the interior of the corrugated plastic pipe is much rougher than the interior of a clay tile. We also need to look at velocity criteria when we're designing drainage systems, and especially underground outlets. Velocities in excess of the allowable may induce piping of soil material into the drain line. This was probably more critical for clay tile lines than it is for plastics, but we still need to meet our criteria. If the velocity is slow and we have quite a bit of sediment in the tile water, that can settle out and collect in the drain. The subsurface drain standard provides maximum and minimum velocity criteria based on soil texture. And here's the chart from their 606 standard. Many of the Iowa soils will fall in the silt loam and silty clay loam textures So you can see that their typical velocities would be here in the 5 to 6 inch range, the typical maximum velocities that are allowable in our drain pipes. If sedimentation is judged not to be a problem, the minimum velocity is 0.5 feet per second. But if sedimentation is a hazard, we have a minimum velocity of 1.4 feet per second. A higher velocity will allow less sediment to settle out into the tile. So let's do another velocity calculation. If we know the capacity and diameter of the pipe, we can do the velocity calculation pretty easily. And as I mentioned before, the design software, charts, and graphs generally provide the velocity in a pipe, and there are those design considerations. But we'll just run through this here to illustrate the process. In this example, our velocity equals our capacity divided by the area. So our velocity is 0.47 CFS, and our area is 0.35 square feet, giving us a velocity of 1.34 feet per second. And if you'll remember back to the engineering field tools printout, well, that's the same velocity that it gave us. And when we're looking at maximum velocity criteria, this is based on the pipe flowing full. And we see that if we remember our table of maximum velocities, this is less than all of those, so this should be stable for all soils. And but it's less than a minimum velocity criterion if sediment is a hazard. So if we have sediment as a hazard, we may be a little bit in trouble, although it is just below the 1.4 feet per second criterion. The Iowa Drainage Guide provides this information about minimum grades to use when sediment is not considered a hazard. So that ranges from 0.05% to 0.1% grade. So you can see those are pretty flat grades, and you can see why that we like to specify elevations and grades to the 100th of a percent or 100th of a foot elevation. So let's come back to the question, how many acres can an 8-inch pipe drain? So to do this, we're going to need some additional information, what pipe material, although I guess we've already decided we're going to use corrugated plastic pipe in our other calculations. But the main question is, how much water do we want to drain from those acres? How fast? The drainage coefficient answers the question, how much water do we want to drain and how fast? The drainage coefficient is the topic of another of our subsurface drain design training modules. Once we decide on the drainage coefficient, we can calculate the flow needed. So the drainage coefficient is basically the depth of water to be removed from the drainage area in 24 hours. Typically we're going to use 3/8 or 1/2 inch for drainage, subsurface drainage in a typical agricultural field. This is a system that will not have any surface inlets. So selecting the 1/2 inch drainage coefficient, our capacity for 1 acre needed for 1 acre is 0.5 inches divided by 24 hours times 1 acre. We need to convert that to CFS because that's how our pipes are rated. So we can put in 0.5 inches divided by 24 hours and put in the conversion factors to convert this to CFS. And we'll find that our capacity needed to drain 1 acre at a 1/2 inch drainage coefficient is 0.021 CFS per acre. If we look at those Ohio NRCS charts I mentioned earlier, we can see for 1 acre at the 1/2 inch drainage coefficient, it also gives us 0.021. So we managed to run our calculator correctly. So let's answer the question, how many acres can we drain with an 8-inch corrugated plastic pipe? Using the N value, Manning's N of 0.15 on a slope or grade of 0.2%. The capacity of that pipe is 0.47 CFS. And our drainage coefficient is 1/2 inch or 0.021 CFS per acre. So if we divide 0.47 CFS by 0.021 CFS per acre, we find that the area drained with that 8-inch corrugated plastic pipe is 22.38 acres. So we can say that an 8-inch corrugated plastic pipe has capacity to drain 22 acres at a drainage coefficient of 1/2 inch. So this concludes our module about calculating the capacity of a drain pipe. To summarize what we've covered in this session, we've learned that the pipe capacity depends on the size, roughness, and grade of the pipe. We reviewed Manning's equation for gravity flow and looked at Manning's N for some different drain materials. We defined and calculated the hydraulic radius and defined and calculated the grade. With that information, we calculated the flow capacity of an 8-inch pipe flowing full under gravity flow conditions. And we determined the area that could be drained by an 8-inch corrugated plastic pipe on a 0.2% grade, given a drainage coefficient of 1/2 inch. So I hope you found this module helpful. Please call or email me if you have questions or comments about this subject. I'm always looking for ways to improve these modules. Good luck.